Hello, this is Induja working as an assistant professor in the Department of Chemical Engineering, Hindustan College of Engineering and Technology. So, in this topic, we are going to learn about what is fundamental property relations. And so, there is three types of fundamental property relation. One is reference property, energy property, and derived property. So, we are neglecting derived property. So, we will learn what is reference property and energy property here. And we will see the Maxwell relation. And before going to see the Maxwell relation, we will see what is fundamental property relations. And by using fundamental property relation and mnemonic diagram, we will learn about what is Maxwell relation. So coming to the introduction part, we will see the thermodynamic properties and what are the types of properties. So you can see the thermodynamic properties of fluids cannot be measured directly, so that necessitates relating such properties to measurable quantities. So in this topic, that is thermodynamic properties, fundamental property relation, we are going to see some new thermodynamic functions are introduced and the equations giving the interrelationship between various thermodynamic properties which are discussed. So here, what are the types of properties? So types of properties are the primary properties, or we can say it as reference property, and energy properties. So energy properties, and third one is derived property. So we are not going to see about what is derived property. So in the derived property, we will see the specific heat, coefficient of expansions, and Joule-Thomson coefficient, and the coefficient of compressibility. So apart from that derived property, we will see these two, that is primary property, which is also known as reference property, and energy properties. So in primary property, uh, that which states that the properties are the ones that are used to define the state of the system, and they are absolute values as against energy properties, which are measured relative to some arbitrary reference state. For example, for the reference property or primary property which are given here, one is temperature and pressure, volume, and entropy. So of these, temperature and pressure are intensive, and volume and entropy are extensive property. And in addition to these, in dealing with the solution, the composition is also treated as reference property. And coming to the energy property, so the energy property is have the four energy properties, that is internal energy, Gibbs free energy, Helmholtz free energy, and enthalpy. So these are all extensive thermodynamic property and are also known as relative to some reference state. So these are referred to as the energy properties that changes in in these functions, that is thermodynamic functions, indicate useful work under certain conditions of restraints. So these are the types of properties. Coming to the mathematical theorem. So here we are going to see about the mathematical theorem like fundamental property relation and Maxwell relations. So here first theorem, so this part says that the what is canonical variable. So canonical variable, here we are taking it as z as a function, that is dz, so which is the function of x comma y comma z, then may be exposed as a function of x and y. So here dz will be equal to so the function is dou z by dou x of y into dx plus dou z by dou y of x into dy. So this is what the exact differential equation we will solve. So in this method, so let z be a single valued continuous functions of two independent variables, that is x and y. So that is z is equal to the function of x comma y. So dz is equal to, so this term dz by dou x divided by dou z divided by dou x of y is equal to m. and we are considering dou z by dou y of x is equal to capital N. So we will write as dz is equal to m dx plus n dy. So where is it? M and n are functions of x and y, and we are differentiating m partially with respect to y and n with respect to z. So we are differentiating m with respect to y. We will get dou m divided by dou y of x is equal to dou square z by dou x into dou y, and with and we are differentiating n with respect to x, we will get dou n divided by dou x of y is equal to dou square z by dou y into dou x. So since this both are same, so we will say it as dou m divided by dou y of x equal to dou n divided by dou x of y. So this form is known as the condition of exact differential equation. So in thermodynamics, this relation forms the basics for the development of Maxwell relation discussed in the next session. So we will see the Maxwell relation while considering this exact differential equation. So before going to know about what is Maxwell relation, we have to know about what is fundamental property relations. So the fundamental property relation is nothing but the differentials of energy properties from the basics for the derivations of a large number of equations relating thermodynamic properties. So these are developed below for systems of constant mass and composition in which the only external forces in the pressure and the process occurring is reversible. So we will know we are already know about what is the first law of thermodynamics for non-flow process, that is du is equal to dq minus dw, right? So we are going to derive by using that first law of non-flow process. So in the fundamental property relation, we have four equations. One is internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. By these properties only, we are going to derive the Maxwell relation. So this equation is fundamental property relation. By using the first law of thermodynamics for non-flow process, we can see that du is equal to dq minus dw. From this equation, we will get the fundamental relation, that is for internal energy du is equal to TdS minus PdV. For enthalpy, dH is equal to TdS plus VdP, and Helmholtz free energy dH, or we can say it as dF. So most of the books have given as dH is equal to minus PdV minus SdT, and for Gibbs free energy, we will say it as dG is equal to minus SdT plus V into dP. So we have learnt about what is the fundamental property relation for four equations: internal energy, Gibbs free energy, Helmholtz free energy, and enthalpy, right? So from this fundamental property relation, uh, only we will solve. If we know about the fundamental property relation, it is very easy to solve the Maxwell equation. So what is Maxwell equation? So Maxwell equations are helpful in replacing unmeasurable quantities appearing in thermodynamic equation by measurable quantities. So here first point is that thing. So Maxwell equations are helpful in replacing unmeasurable quantities appearing in thermodynamic equation by measurable quantities. So using these relations, the partial derivatives of entropy with respect to pressure and volume are expressed as derivative processing exactly. So it is easily identifiable and physical meaning for four Maxwell equations. It is derived from the exact differential equation. So we are considering the exact differential equations for internal energy, that is at constant volume, it can be said as dou U divided by dou S of V is equal to T. So this is given in this equation, dou U divided by dou S of V is equal to T. While differentiating the above equation, so this equation with respect to volume at constant entropy, that is S, we will get dou square U divided by dou V of dou S is equal to dou t divided by dou v of s. So coming to next slide. So yeah, so in this slide you can see the equation for Maxwell relation. So here also given as the fundamental property relation. So the equation that relates the partial derivatives of properties, that is P, V, T, is nothing but pressure, volume, temperature and entropy of a simple compressible system to each other are called as Maxwell relations. So here so the Maxwell relations have four equations for internal energy, enthalpy, Gibbs free energy and Helmholtz free energy. So for pure substances existing in a single phase has only two independent variables of the eight quantities, that is pressure, volume, temperature and entropy, internal energy, Helmholtz free energy and Gibbs free energy. So and any one may be expressed as a function of any two others. So here you can see the fundamental property relation for a pure substances undergoing an infinite reversible process, that is du is equal to TdS minus PdV and dH is equal to TdS plus VdP and dA is equal to minus S into dt minus P into dV, or we can say it's the dF or dA, that is for uh, Helmholtz free energy and Gibbs free energy, and finally Gibbs free energy gives minus SdT plus VdP. So here you can see the U, H, F and G are thermodynamic properties. So uh, for an exact differential of the type is given as dz is equal to mdx plus mdy, so which is dou m divided by dou y of x equal to dou n divided by dou x of y. So which I have already explained in the second slide. So that is canonical from the canonical variable, that is z is equal to function of x comma y. So from this we will see the Maxwell relation. So here is the Maxwell relation. So by using the fundamental property relation du, dh, df and dg, we are applying this canonical variable, that is z is equal to mdx plus ndy. Then we can say it as dou m divided by dou y of x equal to dou n divided by dou x of y. So this term we are applying into the fundamental property relation. So we are applying into the four equations, that is for internal energy, enthalpy, Gibbs free energy and Helmholtz free energy. So here Helmholtz free energy we can say it as A or F, anything we can say. These are the Maxwell relation, that is 11.4 and 11.5, 11.6 and 11.7, which indicates the Maxwell relation for four equations. So first for internal energy, you will get the value of dou T divided by dou V of S is equal to minus dou P divided by dou S of P. And for all the other equations also, you will get that is dH, that is for enthalpy, you will get dou T divided by dou P of S is equal to dou V divided by dou S of T. And for Helmholtz free energy, dou P divided by dou T of V is equal to dou S divided by dou V of T. And for Gibbs free energy, dou V divided by dou T of P equal to minus of dou S divided by dou P of T. So these four equations are known as the Maxwell relations and are extremely valuable in thermodynamics because they provide a means of determining the change in entropy, which cannot be measured directly by using the measuring variable, that is pressure, volume and temperature. It is considered as measurable variable, which is already unmeasurable. So we are using this Maxwell relation by replacing unmeasurable quantities into measurable quantities. So this is what the Maxwell relation indicates. So we can also derive the Maxwell equation by using the mnemonic diagram. So we have already seen the exact differential equation, that is z is equal to function of x comma y. From that we have taken m and y, m and n. So It is one of the technique to solve the Maxwell relation. And another one is by using the Maxwell relation, sorry, by using the mnemonic diagram, we can solve the Maxwell relation. So here you can see the diagram which shows the pressure, volume, temperature, and entropy. So the corner of the triangle shows the properties. So that is canonical variables, that is temperature, pressure, entropy, and volume. And the another one are the properties, that is Gibbs free energy, Helmholtz free energy, enthalpy, and entropy. Enthalpy and Gibbs free energy, Helmholtz free energy, and internal energy. So U is nothing but internal energy, A is Helmholtz free energy, G is Gibbs free energy, and H is enthalpy. So by using this mnemonic diagram, you will get the Maxwell relations. So this is one of the method. So after solving the Maxwell relation, we can derive the differential equation for entropy. So differential equation for entropy we can take as canonical variable like z is equal to function of x comma y. Like that, we are taking entropy is a function of pressure comma temperature. So if we take the pressure comma temperature, we will differentiate in differential form, that is ds is equal to dou s divided by dou p of t into dt plus dou s divided by dou t of p into dt. So here we can write it as so we already know Cp divided by T is equal to dou S divided by dou T of P. That is specific heat formula for constant pressure Cp and constant volume Cv. So for Cp that is given as the equation, and Cv also given as Cv divided by T is equal to dou S divided by dou V of V. So we are substituting that in the equation of entropy, and you will get the formula finally. And for also the function of volume comma temperature, you will get the answer. And final equation for entropy, you will get ds is equal to Cv by T into dt minus dou V divided by dou T of P divided by dou V divided by dou P of T into dV. So this is the final equation for the differential form of entropy. So that's all about the fundamental property relation. And so the fundamental property relation, before going to the fundamental property relation, we have learned about what is exact differential equation. That is canonical variable z is equal to function of x comma y. And we have discussed about what is a fundamental property relation. And by using the fundamental property relation and mnemonic diagram, we have I hope we have learnt about what is Maxwell relation. So the Maxwell relation is very important topic for thermodynamics. So I hope everyone have learnt what is Maxwell relation. Thank you.